we were talking about sequences. We got some way into this. Now let's go further into this topic. So let's talk about the squeeze theorem. Suppose we have sequences AN, BN, and CN, where AN is less than BN is less than Cn, and the limit as n goes to infinity of AN equals the limit as n goes to infinity of Bn, which is equal to L. Let's Bn Cn. Let's visualize this. So we think of sequences, or we're going to visualize sequences living above the integers on the x-axis, right? Let's put our AN in red like this. These guys could be doing something like this. Tending closer and closer to some limit L. This one here. The Cn are above, right? They're like this. They themselves tending closer and closer to some limit L. Okay, and this is L right here. So the fact that they have this limit means that we put any strip around L, we can guarantee that both of these sequences are inside this strip so long as we are far enough to the right. So for all n which are bigger than some particular integer, which depends on the thickness, every single one of these elements of the sequence, both AN and CN, are within this thin strip around L. That's what limit means, right? And the guys that we are interested in are the Bn, right? The Bn are trapped in between. So let's put the Bn as these little kind of crosses like this. They are trapped in between the AN and CN. Yeah? And what can happen to these people? Well, since both the AN and the CN are inside this thin strip, right? And the Bn are in between these two guys, ultimately, the Bn have to be within this thin strip too. And you can just see it from this picture, right? Yeah? Give me a thumbs up if you see what I mean. Okay, good. So what does that mean? That means that the fact that AN and CN have the same limit, which is this blue and the red tending to the same thing, forces the guy which is trapped between the Bn to tend to the same limit too. So, or I measured then. The limit as n goes to infinity of this guy Bn equals L as well. So this is sometimes useful for finding particular limits that are otherwise harder to do. Let's do an example. Example. Suppose we have this sequence. AN equals -1 to the n over n. Yeah? And we want to show that this thing has a limit, right? So if we think about how this guy looks, its sign is alternating. So for n equals 1, it's -1, right? Over here, for n equals 2, it is positive a half. N equals 3, it's minus a third. N equals 4, it is positive a quarter. So it's oscillating up and down like this, right? Yeah? But from this picture, we get some idea how to handle this guy. We know that this guy is trapped between the sequence minus 1 over n and the sequence 1 over n. Yeah? And both of these sequences, we for sure know tend to 0. Right? And the limit as n tends to infinity of 1 over n equals the limit as n goes to infinity of minus 1 over n is equal to 0. I mean, this is completely analogous to the squeeze theorem you learned when we were discussing the limits of some function, right? We trap something that we don't understand so easily between two things that we easily do understand. So the classic limit for functions, or the classic example for functions, was something like this. So for functions, if we had f of x was x squared sine of 1 over x, right? That's a really crazy function to try and understand because this thing is oscillating so fast. So it does something like this, right? And it's very hard to get a kind of handle on what's happening as we approach 0. But this guy is trapped underneath x squared and above minus x squared, so we can understand the limit as x tends to 0. This is the classic example of applying the squeeze theorem for functions you must have learned, right? Does this seem familiar? Yeah? Cool. And this is the same principle, except now we're considering sequences, and we're trapping a sequence that might be hard to understand between two limits. Yeah? Yeah. So in this case, maybe you think, okay, well, it's not such a big deal. Perhaps I could have handled that some other way, but we can create a worse sequence of, or, for example, if we consider something like this, if we let, say, an equal sine of n over n, then that's really strange because it's really not so clear what the sign of, whether it's positive or negative sine of n, right? So that's harder to plot, and we don't know where this is going. Nevertheless, we still have that minus 1 over n is less than an is less than 1 over n. Yeah? So we still know limit as n goes to infinity, sine of n over n is equal to 0. And there's no algebraic thing you can do to actually show this limit. All right? There's no kind of simplification of the expression or anything. But you can easily make this observation. This is obviously true, and then the squeeze theorem gives this straight away. So this is not just a kind of academic theorem that it's just for general knowledge. This is useful. There are sequences we can give you where there's no other obvious way to understand the limit. Theorem. Suppose sequence an has limit L, and I'm going to write down explicitly what it is, i.e. limit as n goes to infinity, an is equal to L, and f is continuous at L. Then the limit as n goes to infinity of f of an equals f of L. Okay. As always, the picture is easier to understand than this statement written in the language maths. As I erase the board, try to draw for yourself a picture that describes what this is saying, and the picture you'll draw will also describe why it's true, and then you'll see the picture I give you after I this is the statement again. Let's just put down the information. So we have a sequence such that the limit as n goes to infinity of an is L, and we have a function f which is continuous at L. Oops. And our conclusion is that the limit as n goes to infinity of f of an is f of L. Okay, let's draw pictures to explain this. So let's draw a picture to explain the hypothesis, which is, oh, by the way, please write here in the chat so that I can see how many of you are attending. Let's draw a picture to represent this hypothesis right here. What's the picture? Here is L, right? And our sequence is tending closer and closer to L, right? So it's perhaps doing something like this, right? It's trapped closer and closer to this limit L. That's what we've got, right? Let's draw a picture. So let me outline this. So this thing is represented by this picture, okay? And we have the function f is continuous at L. Let's draw a picture to represent that. So what is that? Here we go. Here is our x-axis. Here is L. We have some function, and it is continuous at L. So the way I've drawn it is continuous everywhere, but good enough. It's continuous at L. Yeah. Here is L. It's continuous at L. Yeah. And our claim is that the sequence f of an tends to f of L. And we're going to use these pictures to put together this information to conclude this, okay? So what are we going to do? Well, what are these guys f of an? That's when we take an, we apply f to them, yeah? Yeah? Which is what happens when we consider an being here on the x-axis where we apply the function f to it, yeah? So let's consider what these guys look like when we plot them here. Well, as n increases, these guys get closer and closer to L. That's what this picture shows. So maybe A1 is here, maybe A2 is here, but these guys get closer and closer to limit L, right? So they're getting squeezed more and more around some tiny neighborhood, some tiny interval around L, yeah? So let's say this is AK right here, yeah? And then we take this AK, some arbitrary element of the sequence, and we're applying f to it, right? So if we apply f to it, then it goes up here, right? So this guy is sent to this, right? F of AK, right? And as this AK gets closer and closer to L, as it must do as k increases, we can see from the picture that f of AK has to tend closer and closer to this line here, right, which, because f is continuous at L, is f of L. Yeah? So if we take our sequence f of an, right, yeah, it means we're taking our elements here, and for n very large, it is very, very close to L, and then we're applying f to it. And because f is continuous, which means that as we approach L from either side, you know, f of x gets closer and closer to f of L, that means that these guys are sent here. You can just see it from the picture, right? You just see it. Yeah? So in particular, if we drew any horizontal strip around this, we could see that for all large enough k, f of AK is inside this strip around f of L. In other words, this is true. Right? In other words, this is true. So this red thing, red box, is this information, you know, plus the fact I'm plotting in what happens to f of AK, f of an, whichever subscript you want. Yeah? So I claim that while this might seem like some kind of complicated thing, you know what this means. You draw the picture. You know what continuity means. You draw the picture. You put these pictures together. You have what this is saying. There's nothing complicated about this. There's nothing difficult. This is just a language to explain these pictures. And these pictures you understand. These pictures are clear. Yeah? This is all you have to do to understand 89% of calculus. The only thing that can't be done in this way is this algorithmic part, which I can't explain to you in pictures. But all of the principles, all the theorems, all the meaning of everything, it's all pictures. It's all pictures. Okay? Cool. All right. So we believe this, and then we can use it. We believe it, we understand what it means, and we can use it. So let's do an example. Example 9. The limit as n goes to infinity of sine of pi over n. This shouldn't, so this shouldn't be too hard, but this kind of stuff does throw off a lot of students because they don't have a picture, because they're trying to memorize things. I don't want it to throw off any of you. I'm claiming that all of you will be able to understand this if you look at these pictures. If you're willing to spend 10 whatever minutes looking at this until it just, like, some sort of fog will clear and this will make sense to you if it doesn't make sense to you straight away. If you're willing to spend that 10 minutes, there will be no problems with this kind of theorem or these kind of exercises. So let's look. So what is this? We have a function, sine, acting on a sequence, pi over n. Yeah? So we know that this function here is a continuous function everywhere. Yes, we'll have no problems applying this theorem. Yeah? And if we think about what pi over n is tending to, it is tending to 0. Yeah? Yeah? And for sure, sine is continuous to 0, it's continuous everywhere. Yeah? So by application of the theorem, what we know is that this limit, star, so let me just write actually the full thing. The limit as n goes to infinity, sine of pi over n, should be equal to sine of the limit of the sequence, which is 0, and sine of 0 is 0. Just applying the stuff. But I don't want you to apply this like some memorized rule. The way I want you to think about this is to, in this individual case, come up with a picture in your head. And the picture you should be coming up with is that pi over n is a sequence which goes down like this. This is pi over n. This is the sequence pi over n. And you know what sine looks like. Right? So sine looks like this. So you're taking these guys which are tending towards 0 and you're applying them here, right? They live here, close and close to the 0, and you're applying sine to them. And you're being sent to this part of the graph like this, right? And you see as you get closer to 0, you're being sent closer and closer down to 0 itself. That's how I want you to think about it. I want you to think of these pictures. Yeah? And then you will not get this wrong. You will not get this wrong. Okay, good. So this is one of the harder things in the topic of sequences, and I claim it isn't that hard. It is just drawing pictures. All right, let's do this example, example 10. Sometimes we have to just look at expressions and try to figure out what the limit is from kind of algebraic observations. So this is the question. Does an equals n factorial over n to the n converge? Okay, so solution. Let's look at this guy, an. What is this? This is n times n times n times blah, blah, blah. There are n of these n times. There are n products of n in n. God, that's totally wrong. Let's do that again. That was the denominator. What is this thing? N factorial is n times n minus 1 times n minus 2 all the way down to 1. That's what n factorial is. Yeah. And what is n to the n? That's n times n times n, n times. So it's n times n times n times. Yeah? So if you look at this, the first thing you should observe is that the denominator is bigger than the numerator, right? because there are n terms in the product on the top, right? And the biggest one is n, and then they decrease. Yeah, and there are n terms on the product on the bottom, but they're all size n. Yeah, so your initial observation, just from writing out what these things are, should give you the feeling that this thing is smaller, right? And the issue is it getting smaller and smaller compared to the denominator as n increases? And that's what we're going to think about. Well, how are we going to do this? Let's just look at these guys more carefully. If we look at this guy, it's cancelled by this guy. So that's easy. Let's just kill that thing. Yeah. And if we look at this next term, n minus 1, well, let's not cancel it. Let's keep it. N minus 1 is smaller than n, right? N minus 1 is smaller than n. So yeah, so if we look at this matching of the second term on the top with the second term on the bottom, then we have something which is less than 1 right here. Yeah? And if we look at the next thing, we have n minus 2 over n, which again is smaller than 1. Yeah? In fact, every matching of the term on the top with the term on the bottom is going to be something less than 1. Yeah? Yeah. So the second to last term will be, let's make it a little bit bigger. The second to last term will be 2, and then the last term is 1. And the second to last term is n, and then it's n again, right? So if we match terms like this, we have that this is again less than 1, right? So we could have rewritten this as n over n times n minus 1 over n, and so on and so on and so on, all the way to 2 over n, and then the final term is like this. So that's just rewriting the stuff, right? But look at this. All of these guys here, every single one of these guys here are less than 1. So we're producting all these terms, n minus 1 of them, all of them are less than 1. Doesn't matter if there's n minus 1, actually. It just matters that we're all producting these positive terms less than 1. Yeah? So this entire thing has to be less than, has to be less than 1 over n itself. Yeah? Cool. All right. Tell me how I proceed from this. How do I proceed from this? What can I conclude from this? So the question is, does this thing converge? What do you think now? So I agree it's underneath the graph, or underneath the sequence 1 over n. But we need more than that, right? What else do we need? So when we squeeze something, what do we need? How many sequences do we need when we think about the squeeze thing? We are squeezing something. But to squeeze something, we need 2 sequences to squeeze something, right? We need 2 sequences to squeeze something. So for example, minus n is less than 1 over n. Yeah? But that's not going to work for us. Minus n doesn't converge, right? So it's not enough to be underneath one of these guys. We need to squeeze it, yeah? So how can we squeeze this guy? We've got something which bounds it above. We need to squeeze it from below. What do we squeeze it by from below by? Can you think of a sequence that bounds this guy from below that is easier than negative 1 over n? Look at this. It's perfect. Just 0. Just 0, right? Let's make our other sequence 0. Yeah? Then, sure enough, our guy an is squeezed between these 2 sequences, because this thing is always positive, so it's always bigger than 0, and it's always less than 1 over n. So by the squeeze theorem, since 0 is less than an is less than 1 over n, it does converge. Okay, cool. All right. Okay, let's do this one too. Consider the sequence example. What about if we have an equals r to the n? Okay. For what r does this sequence converge, and what does it converge to? Okay, I'm going to raise the board and want you people to think about for what r does this thing converge and what does it converge to. And if you can't find, I mean, maybe you can't find, quite likely you can't find the answer for everything. You can't find the entire range of r for which something happens or something doesn't happen. Just tell me some r that you know something happens, okay? Find as many of those r for which you know that thing happens, and then find some r which that thing doesn't happen, and then from that sequence of smaller steps, try and come up with this answer, okay? And let's try and spread around the answers. So ideally, someone who hasn't answered one of my questions. Excellent, yeah. So our sequence is this. an is r to the n, yeah? And our second, well, the things that we've been told is that if r equals 1, it converges for sure, because 1 to the n is always 1, it's converging to 1, yeah? And the second thing suggested is that if r is a small number, I guess you mean positive number, right? Between 0 and 1, yeah? And that's also true. If it's some number between 0 and 1, and we keep multiplying it by itself, right? Then it's going to get smaller and smaller and smaller, it's going to converge down to 0, yeah? For example, take a half, we go from a half to a quarter, to an eighth, to a 16th, and so on and so on and so on, yeah? But even if we take 0.9, multiply 0.9 by itself over and over and over and over again, right? It's going to converge down to 0. You see what I mean? Yeah? Cool. So, for r equals 1, it's true. In fact, it's true for any r between 0 and 1, but can we extend that? Do we really need it to be between 0 and 1? Yes, good. So, or between -1 and 1, because if we just look at this, so r to the n will tend to 0. If it's some negative number, then it's going to behave almost exactly the same way as if it was a positive number, except it's going to alternate. So when n is odd, it's going to be a negative small number. When n is even, it's going to be a positive small number. So for example, if we had minus a half to the n, then we're going to go from here. Actually, let me write down the sequence. If we have minus a half to the n, then we have minus a half, a quarter, minus an eighth, a 16th, and so on. So it's just going to alternate up and down, up and down, up and down, but getting smaller, tending towards 0. Yeah? And that's true for anything which is strictly bigger than -1. Yeah? So actually we can contain that, what we know in this statement. So we know that for r, which is between -1 and less than or equal to 1, it's going to work. It's going to converge. What about if r is -1? Will that work? Will that work? Come on. Someone hasn't spoken yet. Will that work? Come on. Excellent. Yeah, good. You guys are doing great. So -1 to the n, let's visualize it. When we have -1, we just have, sorry, when we have n equals 1, we have -1. When n equals 2, we have 1. When so this is 1, this is 2, when you have 3, it is -1. So it's just going to keep alternating up and down, up and down. We're not trapping this close to any limit, right? So n to -1 does not converge. Okay, let's think about values that we haven't considered yet. So we know everything about this story when n is between -1 and 1, right? We know if it's strictly bigger than -1 but less than or equal to 1, it does converge. We know that when it's equal to -1, it doesn't converge. Now we have to think about values which are strictly bigger than 1 or strictly less than -1. What happens then? What happens then? Yes. If r is strictly bigger than 1, it's just going to get bigger and bigger and bigger. It's going to blow up to infinity, right? So consider r is equal to 2. Yeah? Then we have 2 to the n. We have 2, 4, 8, 16, and so on is blowing up, right? Yeah? Or even r is equal to 1.01. Yeah? It keeps getting bigger. Keeps getting bigger. It blows up. Yeah? It blows up. Yeah? It blows up rather fast. It's actually the exponential function. Okay, so definitely not true when r is bigger than 1. What about when r is strictly, let me say that better. Definitely not true when r is strictly bigger than 1. What about when we have r is strictly less than -1? So diverges, does not converge. What about r strictly less than -1? Come on, think. That's the last thing for us to understand. What about if r is strictly less than -1? Visualize it. What do you see happening? Yes, well, it will oscillate where for the n which are even, it'll tend towards positive infinity, and when n is odd, it'll tend towards negative infinity. So consider r equals -2, then we're going to have -2, 4, -8, 16, -32, right? So we'll have that for the even n, we're blowing up like this, and for the odd n, we're blowing down like this. So it's failing to converge again, and it's failing in a very spectacular way in this way. Yeah? Cool. So we understand everything, right? So, full answer is that converges for -1 -1 less than r less than or equal to 1, and otherwise does not converge. So not converging is called diverging. Okay. We're nearly out of time, but I want to finish the topic of sequences. If you have to leave, leave whenever you want. All right, so let's talk about what it means to be monotonically increasing or monotonically decreasing. So we say a sequence is monotonically increasing if and only if an plus 1 is bigger than an for all n. So what does that mean? That means each guy is bigger than the guy before. So if this is A1, A2 is bigger, A3 is bigger, A4 is bigger. It's a clear, obvious geometrical meaning, right? And we say let's call this sequence an. That's Bn is monotonically decreasing. So I'm going to write mono dot is what you'd expect. If and only if Bn plus 1 is less than Bn. for all n. So if it's decreasing, you can see what that means, right? So this is an increasing guy, an. If it's decreasing, then each term is below the last term. It might just be slightly below, but it's definitely below, right? That's decreasing. This is Bn. Cool. So let's do an example. I'm running out of space. Example, show that this sequence an equals n over n squared plus 1 is monotonically decreasing. Okay, write down this sequence and try. I see why you say that, but no, because we could have some sequence that behaves very much like it, but it just takes one guy to break this thing to stop it being monotonically decreasing. So there's nothing we can really trap it between or compare it to for this to fail. So by looking at other sequences, we're not going to get much. We're going to have to work with this guy alone. So there's two methods. The first method is just to fight with the algebra, okay? Because we know what this thing means, right? We know what it means. So sequence is monotonically decreasing. So an is mono decreasing if and only if. So if and only if means so let me put this up here. If and only if means that statement A is equivalent to statement B, which you write like this. So statement A implies statement B, and statement B implies statement A. Okay. So this arrow means logical implication. So A implies B, and if B implies A, we do this. And we have a definition. We write if and only if we do this arrow because that's what the thing means. Okay. So an is monotonically decreasing means that if we take an plus 1, this thing is going to be less than an, right? Now, let's put in the definition of an, right? This is n plus 1 over n plus 1 squared plus 1 is less than n over n squared plus 1. Yeah, that's just what these sequences mean, right? That's what the definition is. So this statement is the same as this statement, logically the same. Yeah, cool. No, not quite, because I miswrote it. Like this. Yeah, everybody with me? Give me a thumbs up if you're with me. Do this if you're not. Cool. Okay. Well, then let's mess around with this. We can multiply both sides by n plus 1 squared plus 1. Yeah? And we can multiply both sides by n squared plus 1. We can do that. And that's not going to change anything. These are all positive things. It's not going to change the sign of the inequality. It's not going to change the direction of inequality. Right? So this is the same. Let's multiply both sides by n plus 1 squared plus 1. So this is the same as n plus 1 is less than n times n plus 1 squared plus 1 over n squared plus 1. It's logically the same. This statement's the same as this. Yeah? Thumbs up if you're with me. Speak up or give me another signal if you're not. Okay, cool. We do the same to this. Let's multiply this on the other side. So this is logically the same as n squared plus 1. n plus 1 is less than this. Now let's expand this out. So we expand this out, we're going to have n squared plus 2n plus 2. Yeah? Now let's just do the algebra and unpack what this says. So if we multiply this thing through, we're going to have, let's multiply through the n, we're going to have n to the 3 plus n. Let's multiply the 1. We're going to have n squared plus 1. That's multiplying this thing out. And this is meant to be less than this thing that's multiplied out. This is n to the 3 plus 2n squared plus 2n. Yeah? Cool. So this statement is the same as this, the same as this, the same as this, the same as this. No? Let's see if we believe this statement. Well, we can just kill the n to the 3, right? Get rid of that. Yeah. And then what do we have? Then we have the statement that 2n squared plus 2n is bigger than n squared plus n plus 1, for all n bigger than equal to 1. Well, I believe that too, because I can subtract n squared from both sides, and I can subtract n from both sides, and then this thing is logically the same as 1 is bigger than n squared plus n, and that's it. Yeah, so I subtract n from both sides, and I subtract n squared from both sides, and then that's what I get. Yeah, and that statement is true. That is true. N squared plus n is bigger than 1 for every n bigger than or equal to 1. That's true. Yeah, so this is true, which implies this, which implies this, which implies this, which implies this, which implies this. So it is a decreasing sequence. Yeah. So that's one way. That's one way. Okay, I'm going to raise the board. Think about if there's another way. Think about if there's another way. This guy. So an is n over n squared plus 1. Okay, let's draw a picture. So n is equal to 1. We're going to have 1 over 2, so it's a half. N is equal to 2. We have 2 over 5, so it's a little bit down like this. Yeah, and so actually we already know it's decreasing, so it's going down like this. But how are we going to show it's decreasing without actually doing this stuff with the algebra? Let me make this picture more clear. So this is 1, this is the next one, this is the next one. So it's going down like this. What other way do we have? Generally, what way do we have to show something's decreasing? Just if we're talking about functions, for example, how would we show it's decreasing? The derivative, right? If the derivative is negative, the slope is negative, and it's going down, right? Yeah? Is there a way we can use that for this? Yes, but here we have a sequence, right? So we can't differentiate it. So we're going to have to add something in the mix, right? Perfect. We're going to make a function to recover the behavior of the sequence. If we have a function like this, where the sequence lives on the graph of the function, you know, so your word model actually is quite okay. Except model sometimes implies a kind of approximation, where this is not approximation. Actually, want a function that lives on this sequence, yeah? And if we know that this function is actually decreasing, then that would show that our sequence is decreasing, which we can just see from the picture, right? If the function is decreasing, then these points of the sequence that live on the graph also have to be decreasing. Do you see what I mean? Yeah? Give me a thumbs up if you see what I mean. Excellent. All right. So our job now is to come up with a function that's going to recover this sequence. What function will do that? Let's write down in the language of maths what that requires. So we want function f such that f of n is equal to this thing, right? N over n squared plus 1. Because if f of n equals this thing, that's exactly what this picture is showing us, right? Because here is 1, here is 2, here is 3, and the statement, or this expressing what this picture says, that these points of the sequence live on the graph, is exactly in the language of math saying this. Yeah? It's saying that f of n is equal to the elements of our sequence. Do you see what I mean? Okay, cool. And the advantage of expressing in the language of maths what we want, yeah, is that it becomes much easier to actually find it, to actually do it. That's the power of this thing. This language allows us to clarify what we want and therefore find it, solve the problem. Okay, look at this. Tell me what function f will do this for us. Perfect. if we let this thing be the function, that thing will exactly do this, right? We stick in n into this, we get this. Yeah? So this is a sentence. Solution, f of x equals x over x squared plus 1 does exactly our job. So if we can show that this function is decreasing, we're all set. So just need to show f is decreasing. And as you people told me, we can show something's decreasing by showing its derivative is negative, yeah? So that's what we're going to do. And now we can use the power of calculus, because calculus allows us to calculate the derivative, see the sign of the derivative to determine if something's decreasing, yeah? And that is much easier than this sequence of inequalities that I did before, because we know how to calculate derivatives. So f prime of x, it's the quotient rule, put everything onto the bottom squared, differentiate the top, we just get 1, leave the bottom alone, x squared plus 1, minus, leave the top alone, differentiate the bottom. Yeah? So what is that? We're going to have minus x squared plus 1, this is over everything squared, over x squared plus 1 squared. And this is indeed less than 0. This is less than 0 for all x bigger than 1. Yeah? So this guy for sure is decreasing. Yeah? It's decreasing. This guy is less than this guy because the function is decreasing for every x bigger than 1. Do you see what I mean? And that is easier and faster than what we did before. So there's a real advantage in taking this perspective, right? So keep this in mind when you're asked to show that a function is decreasing. You could either, keep this in mind when you're asked to show a sequence is decreasing. You could either fight with the sequence itself or just do this. Yeah? Cool. All right, I have one more thing to tell you about increasing, decreasing sequences, and then we're done on this topic. So next thing is definition of bounded. So we say a sequence is bounded above let's put a line around this stuff. If and only if, let's go with the sequence a name, there exists M such that AN is less than or equal to M for all N. And again, this is straightforward to visualize, right? So this is M, all of our guys are our sequence, all the elements are underneath it. Yeah, that's clearly the meaning of this. Yeah, and we say something is bounded below a sequence Bn is bounded below if and only if we have the following is true, that Bn is bigger than or equal to little m for all n. So again, that's easy to visualize. We have some m here. It doesn't have to be negative, could be positive, just drawn it this way, such that all the elements of our sequence are above this guy. Right? So here is a true fact. Theorem. If sequence AN is increasing, so I'm not going to say the word monotonically because I'm just saving time. It's monotonically increasing and bounded above then an converges. So the limit n goes to infinity, an exists, i.e. an converges. Okay, take a fresh sheet of paper and then draw a sequence that is increasing but bounded above, and then from your picture try and explain to me why this is true. Do this together. So we have something that's increasing. Okay, it's increasing. Like this. Yeah? But it's bounded above. Yeah? Okay, let's think about what is going to happen, right? So if this is, say, k, then the next guy is a little bit up, the next guy is a little bit up, the next guy is a little bit up, and so on and so on and so on. Yeah? So for sure we know that each of these guys has to be going up by less and less, right? Because if not, if every now and again we jump from ak plus 1, we jump from ak to ak plus 1 with a size, whatever, 0.1, if that happens for an infinite number of ak, then we're going to get above everything, right? No matter how small a step size you take, if you keep taking a step size in a certain direction and do it infinitely many times, you're gonna go to infinity, right? So we know that the size increase from each guy to the next is smaller and smaller and smaller. Yeah? As we're later going to learn, that's not enough to conclude this thing actually converges. We know more than that. We know that if we add together all the step sizes going forward, right? So to consider what happens, how much bigger this guy, let's say this guy is k plus m, is from ak, then it's the step size here, plus the step size here, plus the step size here, plus the step size here, right? Yeah? Then for every m, no matter how far along we go, adding together all these step sizes isn't going to allow us to go to infinity, right? Yeah? So what this means is that you can imagine pulling down this line here. Yeah? Pulling down this line, and as we get closer and closer to this line, which will be the smallest number, which is bigger than all the elements of the sequence, yeah? Then as we go along the sequence, we're getting pushed closer and closer to it. We're getting pushed closer and closer to it. And that thing has to be the limit. So this guy is our upper bound, m. That doesn't have to be the limit. M could be way above everything else. But if we consider the smallest number, which is bigger than all the elements of our sequence, yeah? That number here, whatever that is, L, yeah, is such that as we keep going along, we're pushed closer and closer to it. Yeah? Yeah? If there's a gap between these guys and the number L, then it's not the smallest number, which is bigger than all of them. Yeah? So ultimately, we're being squeezed closer to it because we're always going up, and this is the smallest number, which is bigger than all of them. Yeah? So you can see that we can ultimately guarantee that all the elements of our sequence are within some thin strip of this number L. You see what I mean? Yeah? Cool. So from this picture, we believe that this is true, that if we have a sequence that is bounded and it's monotonic, then it will actually converge to a limit. Watch this over. This is new for you. Think about anything which is unclear. I have my office hour now, so stick around if you want to ask questions. Otherwise, I will see you all on Wednesday. Bye-bye.